Let's get started. So a quick reminder, homeworks are due at the end of Wednesday, and then the project proposals are due on Friday. So make sure to get those in. Okay, so just as a quick review from last time, we went through the sort of step-by-step algorithm of how you would do a step forward regression, and we also talked about the step backwards regression, and now we're going to look at the sort of implementation of that. Okay, and so we're going to start off today on the code side of things. I'm just going to go ahead and load in a couple libraries. Okay, so ggplot and data table we know about. glmnet is actually a package that will let you do some of the forward and backward stuff automatically. And that's the sort of black box version, but we're going to do implement it ourselves in code first before we do that version. And then the last package, ISLR, that's actually a package that comes from a book. Maybe you guys have heard of it, ISLR. It's a well-known, very useful book, Introduction to Statistical Learning. I think that's what it's called. Hang on. Yeah, Introduction to Statistical Learning. Actually, a lot of the material from this course comes from that textbook, so feel free. It's actually really easy to digest. So you can use that as a reference point. And that book is actually available as a PDF on Canvas. So you have access to it already. Okay, and so they walk through lots of examples and stuff, and so they have some nice data sets already, and so we're going to use one of those data sets, which is called credit. And we can actually look at that particular data set here. And so this is a data set pertaining to credit scores for different people. And we can see the different columns and what information is available. So we have information about the person's income, information about their credit limit, about their credit rating, the number of credit cards that they have, their age, gender, whether or not they're a student, whether or not they're married, their ethnicity, and then the current balance that they have on their credit. And so what we want to be able to do, so that's the average balance over the average monthly balance. And so what we want to be able to do is to see if we can relate this particular outcome of the balance against all of this other information that we have about the person. And so we got lots of variables, right? And so how many variables do we have? Where's my mouse? Here we go. So we do have an ID. And then we have our explanatory variable. And then we have the 10 possible, we have our response variable, and then we have our 10 possible explanatory variables. So as we discussed before, right, even when we just have, this is not like a crazy big data set or anything. We have 10 variables. How many combinations of variables could we test out, right? If we're trying to figure out like what's the best model, and we use different variables and different combinations, like how many combinations can we have?
2 to the power 10?
Yeah, about 2 to the 10th, right? And so Okay, we have 1,000 models. So if I were to do these kind of one at a time and type them all out, it would probably we would probably be here for a while. And then if you remember, in the step forward and step backward procedures, it drastically reduces the number of models that we have, right? And so does anyone remember the approximate number of models that I would have to test with a step forward regression procedure?
10 plus 9 plus 8.
Yeah, exactly. So 10 factorial. Does this work in R? I actually don't know. Probably not. Does anyone know the shortcut for factorial? I'm going to throw a Hail Mary here. Oh no. That's not right. 10 plus 9 plus 8 plus 7.
Should be factorial.
Wait, factorial is multiplies, right?
Yeah.
Oh, yeah, sorry. I don't know what this is called. But not 10 factorial, sorry. My brain is mush today.
Cumulative sum?
Yeah, so, right, we have, about 20 times less in terms of the number of models that we would have to test, which is great. Right, and it continues to grow exponentially, right? If we have 11 variables, then this would go to 66, this would go to 2,000, right? Okay, so let us figure out how to implement a step forward regression. So all I'm doing here is I'm pulling out all of the column names that I want to use as my potential explanatory variables. So this is kind of my starting point. Okay, so if I run this includes all of the names in the columns, right, except for ID and except for balance, because we know ID is just an index variable that's not going to be used to explain anything, and balance is our response variable. So we're going to take that out. And so this is our kind of starting point. Okay. So this is probably going to be one of the larger kind of code chunks that we're going to step through. But if you kind of hold on to what we talked about last time, if you have an understanding, right, of how we actually perform the step forward regression, then hopefully this will be all clear for you. Actually, so here we'll start step forward regression procedure. So first I'm going to create a bucket to hold basically all of the models that I'm running. So that's just going to be called all.models. And as we work through, certain for loops, I'm going to just save the results and stick them into there. If you kind of just imagine what we're doing from last time, let me see. Actually, I can pull up the let me quickly just pull this up from before. Oh no. Here we go. Okay, so remember that we go through all of these, we pick the one that has the best R squared, then we go to the next one, and then we pick the best one and we go to the next one. So as I go from step 1 to step 2 to step 3, what information do I need to hold onto as I proceed into my next steps?
R squared.
Not the R squared.
The best model.
The best model. Okay, that's right. Yeah. So you wanna track the fact that, okay, I'm gonna hold on to x2 in my next one, and then in step 2, I want to hold on to x2 and in x3 as I move on to the next one. So you have these, we'll call them selected variables, and that's the information that I'm going to use to pass on between each of the steps. And so that's going to be this other empty bucket that's going to continue to populate as you move through the for loops. So for n in 1 to length credit names, where's the mouse? Oh. Okay. We are going to available names Okay. What do you guys think is going on here? What do you think available names means?
It's to test the explanatory variables that have not been tested.
Yeah, exactly. So in the example that I had, right, in step 1, I store x2, but in the next one, you can't take x2 again, right? You can't test beta x2 plus beta x2. So let's say like income was selected in the first step. I wouldn't try and test income again in the next step. And so I have this pool of available names, which every time I move through the loop, I take out what has already been selected. Yeah?
Can you do this with the unique function somehow?
No?
It takes the unique.
No, the credit names. The credit names is just this list here. So this is already unique. This isn't like the full list. Okay, now I will have something that holds on to the best model, something that holds on to the best R squared. Oops, and actually I'm going to initialize that as 0. And then we'll have something called best name, which will also be empty for now. And now we need to do something like this. Okay, so I have a for loop inside of a for loop. And so why am I doing that, right? If we jump back to here, this is my outer loop, step 1, step 2, step 3, as I proceed in each one of these. And then inside, I have to loop through all of my possible models within each step. So the code is representing that inside loop is like this and this, and this and this, and so on and so forth. And that's why I'm just testing the available names and not the full set of names. So we'll do something like this.
What is collapse?
Yeah, I'll show you in just a second. These two lines. Okay. So let's say I'm in step 3 and I've chosen 2 variables. What are those 2 variables? Let's say the first 2 variables that got chosen in the step board is like limit and cards. Okay? So limit and cards are in the selected variables. So we take these guys out, and the available names are income, rating, age, educating gender, student, married, ethnicity. So everything except for these 2. So these get pulled out, and I'm actually going to take the available names one at a time, right? As I go through my for loop. So it'll be, the first time I go through the loop, it'll be income, limit, and cards, right? Because I'm putting the available names and selected variables together. So it'll be income, limit, and cards. Then it'll be rating, limit, and cards. Then it'll be age, limit, and cards, education, limit, and cards, and so on and so forth. Right? That is what this is doing. And when I paste these things together with the collapse, it will do something like this. So paste C of available names. So we'll do income, limit, cards, collapse equals. So it just sticks a plus in between each entry. And then I'm creating the formula that I'm going to put into my regression, which will be balance regress on income, limit, and cards. Okay. And then I will create a model. Okay. So this inside loop basically runs all of the possible combinations at every step, individual step, right? So limit and cards are the same. It'll be income limit cards, rating limit cards, so on and so forth. And all of this is just to handle that. And at the end, I'm running the regression, and then I'm also holding on to the R squared. Yeah.
What's the sep origin of doing there? Separating the values by space, or?
Which one?
The sep in the formula dot hold.
Yeah, that means that they're not separated by anything. It's just empty.
It's balance, and then the square.
If you don't leave it empty, would the formula not work?
No, they're just putting it so it's right next to each other.
Okay.
So let's do this. Formula, paste, balance, comma, that thing, which is the previous one. And then at the end I have sep equals, sep equals.
You've got no squiggle, but you can put the squiggle in there.
Yeah. So it will generate a formula that you can put in. Okay.
You need to separate.
Now, based on that, I can run the model, and then from the model, extract the R squared, which is done like this. Okay, so thinking caps on. What is going on here? Like, what do we need to do? So someone tell me in English for the step forward regression what needs to happen. So don't worry about the code. Just tell me in English what needs to happen now. So the inside loop, I've run all the models. I've taken all of the R squareds. Yes.
Select the model with the highest R square.
Yes.
Then, basically compare that with the remaining ones.
Perfect. Perfect. Now, not in code, but can you think of a way that you could do that in this context? Can anyone think of a way to do that in this context?
You use the which max command and pick the highest R squared. I'm not sure what the exact.
You could do something like that if you like stored this value every time, but actually we're not storing it. But yes, that is a totally legitimate way to do that. So let's see one way that we could do this. So we need to figure out which one's the best. So on the first time we walk through it, our R squared is just 0. And we say, is the R squared that I just got from my model better than 0? And probably it is. And so I'm going to store everything about that model, right? Because it is better than the best thing that I've observed so far. So I'm going to store the R squared as the best R squared. I'm going to store the variable as the best one. And then I'm going to store the model as the best one. Okay? And now, so you've done income limit cards, and then now let's say you do rating limit cards, and you go through this whole thing again, and now let's say the first time, let's say this had an R squared of 0.8. Let's say rating limit cards had an R squared of 0.75. So what happens here?
It's 0.8. Just one time.
Yeah, it doesn't do anything because 0.75 is not better than 0.8, and so we still maintain that the first one was the best one. And then let's say we go to the next one, age limit in cards, and let's say hypothetically that that one has the highest R squared. Let's say that one has a 0.85. Then 0.85 is better than 0.8, so then we enter here and we say now our best R squared is 0.85, and then we're going to hold on to the variable name and the model. Okay? So it goes through my inner loop, and as it goes through, anytime the R squared of the model is better, it kicks out the old one, right? And then it holds on to the best one. And so once I get to the end of this for loop, this will have the best model from that one step. Okay? And that's all that you need to do for that inside step. And then we go back to our outside step, and all we need to do is we add the best variable that we found from our inside step into our selected variables, and before we move on to the next step. And then I also want to store the best model from that step. And why do I want to hold on to the models? Yes, so that you can compare. Yeah, exactly. Okay. And that's it. And so this code should now be able to run through all the different combinations within each of the steps to run the 55 or so models according to this sort of procedure. Any questions about this? So let's run it and let's see what happens. Ah. Of course. Let's see. Unexpected symbol. All right, who can find the error first? Credit names. Did I define credit names? I did.
No, it's the best model.
Oh, best model hold.
Yeah.
What's going on here? That looks right. Available names. These credit names. In select here. Okay. Oh, this is not a new line
Yeah.
for some reason. Okay, there we go. I love troubleshooting in the middle of class. Okay. Looks like we have. I might have needed to do n-1 instead, but okay. Anyways, I think generally it worked. So. In step 1, as I test each variable individually, the model with the highest R-squared is income. So we select income, right? So income is the thing that has the highest R-squared as it pertains to the model balance versus one variable. And so we take income and we save it and we fold it into the step 2, and then limit and income are the most important. So we take these two and we keep these as we run through all the variables. So then it adds rating, cards and rating, age, cards rating, and so on and so forth, right? And you can see each time we step through, one additional variable is added. And so recall that actually, as you increase in model complexity, right, you do a better job of being able to essentially predict your outcome. But at a certain point, we know what? When you add too many variables, you get overfitting, exactly, right? And so we came up with a bunch of ways to test for overfitting, right? some criterion. So you can do the AIC, you can do the BIC, you can do adjusted R squared, you can do cross-validation, mean squared errors, right? And so I can now go in and apply that to each of these models, and I should be able to see some balance between like a model that's not really that good to a model that's really overfit. You find the best balance of that according to whatever criterion that you use, and you should be able to find that model. Let's see here. So I should have all models. Yeah, okay. So the for loop saved the models one at a time. So like model 5 has 5 variables, model 4 has 4 variables, and so on and so forth. And so now what I can do is apply those higher level criterion to each of the steps to identify the best one, right? And so something like L apply okay, I can use this to see what is the AIC of each of the 10 models. So who remembers the AIC? Is it better lower or higher? Lower, exactly. So if I use the AIC here, we can see the value. So the 8th model has the lowest AIC compared to everything else. So if you're using that metric, you would say, okay, my model here, 10, 9, 8. So this model is the best balance between the explanatory piece of all of these variables versus the like overfitting of having lots of variables, right? Yeah.
So this says for these variables with respect to balance are best for predicting someone's balance. Right. Is that what?
So it depends. So, right. So I would actually say not precisely. I would actually say if you did the cross-validation procedure for mean squared error with out-of-sample testing, then I would argue that that is instead of the AIC, then that would be a better conclusion to draw. But it depends on the criterion that you're using, right? So AIC, BIC, the BIC similarly says that model 8 is the lowest, yes, right? Compared to all of these other guys. And then lastly, if I wanted to do adjusted R squared, it would be something like this. And in this case, I would want to pick the highest adjusted R squared. And we can see, so not so great. And then here, 9539, 9538, 9538. So actually, in this particular case, the AIC, BIC, and adjusted R squared actually all agree that that 8th model, whatever that is, happens to have, you know, the best values for each of these criterion, which is not always the case. You can definitely have slight disagreements between the different criterion that you're using, and that's not unusual or unexpected or anything, right? Yeah, actually the cases that it all lines up is probably, I would almost say less common than if they were all in agreement. So don't be too surprised if you find that. Yes.
If when they don't line up and they're different, what's the right criteria to say, oh, I should trust this one, or I think this one is better to trust this one more, or is it?
No.
Is there that order of magnitude difference from the others, or how different is it?
They'll typically be pretty similar, but like I said last time, they are explaining slightly different things, right? Like the BIC is typically we would argue is a better application to really large data sets. AIC is better application to smaller data sets. And those both are measurements of something slightly different from like an adjusted R squared, which you would be more arguing, like if I were to compare like a adjusted R squared versus like a cross-validation, my interpretation of that might be that this is the model that best captures the variation in the data, right? If I were using adjusted R squared versus this model is the thing that best predicts out of sample if I was doing cross-validation, right? So the interpretation of the best model is dependent on the criteria they're using to select, you know, quote unquote best. What is best about that model?
Could you go back to the original loop code again?
Yeah, sure. Somewhere here?
Yeah, I'm trying to figure out why I'm getting an error. Troubleshooting it's not very helpful.
Yeah, so don't worry about that. It's more important to have a comprehension of the code, and this stuff will all be posted online
Okay.
anyways. So if you have a question about a particular piece of the code or something you don't understand, yeah, let me know. And think of the conceptual translation of what we talked about last time into this code and the approach that I've taken to do this. Homework 3 will have you guys replicating this code, but for backward stepwise regression instead of forward stepwise regression. And the idea is, again, to like focus on the conceptual part of it. I would like translate it to like just English, how you would walk through it before you actually code it. Is the sort of best approach. And of course, what I'll say about this is that obviously you don't need to like write up this block of code every time that you want to do a step forward regression, right? There are functions that do that for you, but we want to understand what's happening behind the scenes. And so the functions, so I will show you guys quickly the ones that will actually do this for you. So, oops. I don't know if I have done this before, but when you run a linear model, you have your response variable here, regressed on, tilde. If you just put a period here, what it will do is it will regress on every other column in the data set. It's a shortcut so that I don't have to type out 10 variables. Or importantly, if I have like 1,000 variables, that I don't have to type them all out, right? So you just put a dot and it says regress on everything. And the way the models work that have built-in functions to do this looks something like this. Step step AIC. This is just one. There's a lot of different functions that you could find that do this. This is just one that I've chosen. I'm using a stepwise regression method in both directions. So this will run it both forward and backwards. And it will use this model to do that. And it knows what variables to put in and take out, right? So the other thing that I'll mention is that similar to the fact that when I run a stepwise forward regression with AIC, BIC, adjusted R squared, or cross-validation, and though the actual model that gets chosen based on the criterion could be different, also, if I run it backwards as opposed to forwards, you could also get a different answer. Okay, so it's always kind of important to try it both ways, try different criterion, really try and land on something relatively robust. Yeah?
So when it's backwards, you start with all the variables?
Yes.
But then how do you
Yep.
choose?
Yeah, so here, let me... So the procedure for backwards goes something like this. I start here with all of the variables and I regress and I find the R squared. Great. That's kind of like step one. Now I go to step two and now I take one variable out at a time and then test all of the R squareds. And then the one with the highest R squared will be my fixed one. And I will have chosen a variable to keep out forever. And then moving to the next step, I will start with this thing, and then I will drop one variable at a time that's in my current list, and remove that, and so on and so forth. Make sense? Yep. So instead of adding a variable every time, you are taking a variable away every time.
Do you need agreement across all sort of criteria? So R squared, AIC, and this. Do you need
No.
consistent agreement across all, or with?
No, you won't get that. It's very uncommon that you would see agreements that model 8 has the best AIC and the best BIC and the best adjusted R squared.
So just make sure they're forward, start with all of them, new.
No. Forward, start with none of them, put them in one at a
Sorry,
time.
yeah, okay.
Backwards, start with all of them, take them out one at a time.
Yeah.
Yes?
How often those two approach kind of come to the very similar model?
It's pretty often that they'll be very similar. It's very unusual that they won't be
Yeah.
super different, but it is a little less common that they all land on exactly the same one. So oftentimes you might see forward says the 8th model is best, and backward says like the 7th model is best, something like that.
Is there a scenario that one of them would be working much better than the other one, or they just?
I mean, it's possible, but it would be uncommon, I would say. But it's definitely possible, because the whole point is that the point of this, right? To like refresher, right? We're testing 55 out of the 1,000, and we're trying to do it in like a informed way, right? Which is why you're taking the best one, then going to the next one, best one. But it could so happen that like some combination of the variables might have been the best that you missed, just because of the way the procedure works, right? Because we take the one and then we omit everything else. And the whole point of doing it forwards and backwards is an attempt to capture possible things that you might miss. And so it may be the case that going backwards, you happen to retain the like special combination that you needed that would have been missed going forwards. And then in that case, maybe the backwards regression leads to a much better result, right? And so maybe you have an adjusted R squared one going backwards that's much higher than the best one going forwards. And that is definitely possible. Yeah.
So the step AIC function is doing the forward without.
Yeah, why don't I run it?
Okay. What's the image of it?
No.
The mass library.
It's mass? Oh man. Okay. Okay, well, let me change that in my notes. Thank you for that. Had a slight panic attack. Okay. Where's my mouse? Here we go. I'm gonna add that up here. And this one actually might be different because the way it treats intercepts might be a little bit different. I can't remember. No, oh, I didn't actually read it. Library mass. Okay. Thank you. So this is going to run through and give you the AIC. This looks like it's going backwards. Yeah, so this way is going backwards. I thought I should do both.
You started with all variables, so the only direction it can go is backwards, right?
I thought it knew to start with nothing. Maybe I'm wrong. Yeah, no, you're right. Wait a minute. For some reason, I'm remembering that this should have done both, but okay, I guess you're right. So then the way that you would start the other one would be just one at a time. So you would just put in one variable and you would say forward, and then it should proceed through all of the combinations. And then to do the VIC, it's the same thing, except you modify the penalty factor like this. This is a way that you can modify the AIC to represent the BIC, and it will do a similar type of procedure. So yeah, so the point is here that there are specific functions that will, implement that big chunk of code that I had just written out. Okay. Yes.
Is it not going to just one variable? It stops it down four.
I think that
Oh, the minuses.
I think it's actually running through everything, but then I think it's stopping when it gets to when the next step has like a higher AIC. So 3705, 3706, these will all be going up, and I think it's stopping because the one after that has a higher value. Yeah, so these ones will progressively print until you get to a higher AIC. Yeah.
So you still use the step AIC function, but you said you changed the penalty. Like, how does the K-log and the
Yeah, so if you,
penalty?
yeah, so if you remember from before, when we look at the different criterion, it's actually the same thing as the AIC, except this penalty function is slightly modified. So it's a way that you can translate between your AIC and BIC is like that modification. Yeah. Okay, actually, we'll go from here. Okay. So this procedure that we've talked about, the forward regression, forward stepwise and backward stepwise, these are classical methods known as subset selection. So classical methods of subset selection stepwise. And so this can be forward or backwards. And so what we're going to talk about for the rest of the day today are different modern methods. So this is known as shrinkage or regularization. And this is very common in machine learning fields. So the two techniques that we're going to talk about are ridge regression and lasso regression. Okay. So ridge regression. So let's go all the way back to sort of fundamentals. We are going to write out actually our optimization problem. Minimize the sum of our squared errors, right, which is this. Yi minus beta 0 minus j equals 1 to p beta j times xij squared with respect to our beta 0, beta 1, dot, 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 beta n. Okay. Someone help me interpret this again. Yeah.
You're taking all the error terms, squaring them, and summing them up together.
Yeah. So this is our actual value, right? And then our predicted, right, is our beta plus beta times x, beta 0 plus beta 1 times x1, right, which is just this thing. And I've just subtracted it over. So this is my error term, right? So if I have a line and I have points everywhere, I want to figure out the slope of the line. So I'm allowed to mess around with my betas. Those are my, like, if this is an optimization, those are my decision variables. So I'm like moving my line around such that the sum of the square of those errors is as small as possible, right? So that is our ordinary least squares thing. Okay. So this is from earlier on in class. And now what I'm going to do is I'm going to modify this regression just a little bit. I'm going to put an extra term here. Okay, let's take this out for a second, and let's think about what this means. So, let's say I have 1,000 betas. Okay. Well, I can almost always reduce the error by introducing more terms, right? You are introducing more degrees of flexibility. I have another beta times x, another beta times x, another beta times x. You're right, like this term here lets you subtract small components of my x's to reduce the error. And so what happens when we do that? If we do that too much? Overfitting. Exactly. So this term here is exactly meant to deal with overfitting. What happens if I have 1,000 betas? What is this term doing when I add more and more betas?
It
Penalizing the little
Yeah, exactly, right? Because we want this to be as small as possible, but as I add more betas, that number will actually get bigger because you're doing a plus. You know, this makes it so that the negative values doesn't matter, right?
Does that say true?
This is a tuning parameter. So a tuning parameter is essentially how much do I care about all of those extra betas, right? So what happens when this tuning parameter is 0?
Okay.
Exactly. So now we're just in a regular linear regression, right? And so as this number gets larger, it says these betas are becoming more and more problematic. So in fact, whereas our classical methods got rid of the betas, what this is doing is that it's actually making it so that the optimization will actually shrink the betas close to 0. In essence, saying, unless these betas for these x's has a really important effect on the model, we're just going to make these values, the coefficient values, really small, right? And so the larger the tuning parameter is, the more it says, oh, let's just, unless the beta is really important to reduce our errors, we're just going to make those coefficients closer and closer and closer to 0 as possible. So that's why we called it shrinkage, because it is regularizing or shrinking the value of the coefficients. So it's a little bit weird to think about, right? Because you're used to, like, when you run a regression, it's just like the coefficients represent the values related to the effect of your variable on the outcome. But in this case, it's like it does that, but it also says taking into account the fact that we don't want to be overfitting. Yeah.
So it's not doing anything to change the number of betas, it's just making the beta smaller.
Yes. Exactly. And in fact, it could, in essence,
If it
kind
goes
of
to
do
0,
that.
then-
Exactly, exactly. So oftentimes what you'll see is that sometimes the betas will get pushed to 0. In essence, what it's saying is like, get rid of that variable. Right? Yeah.
Guess I'm talking about the same thing. So this kind of just only penalize those the x with a smaller beta, but really doesn't penalize the number of x included in the model, right?
Yeah. So what you'll see is that I could throw in 10,000 variables into my ridge regression and then see which ones get shrunk away to 0. And then you can mess around with your tuning parameter to figure out different ways of like penalizing your betas. Okay, so let me put this question to you guys. How do I choose my tuning parameter? Is there something that we have done before that might make sense to think about how to calibrate this? Cross-validation, exactly, right? I can run this tuning parameter from 0 to 1 or whatever value, and I could do it a bunch of times And the closer to 0 you are, maybe you're doing a little bit more overfitting, and then the closer and the larger this is, maybe you're doing underfitting, and so you want to hit that sweet spot. And so the way that I would figure out my tuning parameter is through something like cross-validation, right? And this is analogous to the classical model, right? I'm using something like a cross-validation to figure out how many variables to include. The question of how many variables to kind of include, right, is kind of captured by the tuning parameter, and so that same procedure of like running cross-validations is what you can do to get your lambda, yeah.
Could you explain how is it shrinking all the other betas if you break open the brackets, and how is it mathematically shrinking the other betas in the near the RFS term?
If you got rid of this, and it just calculates a beta, right? So we know how that works. So let's say you're really in, man, this thing just does not want to stay on. Okay, let's say you are in serious overfitting territory. It can alter the betas to like get rid of unnecessary ones, right? It can shrink the value down. Yeah.
So that last term is actually part of the summation is up front, right? That's what is your I?
No. It should be, it'll be like this. Yeah. So betas that have an important effect will try to stay close to true value. Betas that are not important will shrink. Yes?
So it seems that in the equation it's only penalize those beta based on the value, but in the regression results it also has a p-value to consider whether the effect is statistically significant. Does this equation capture that?
Yeah. Good question.
Maybe in the error part.
It will, so the standard error parts actually don't, so they're taken into account here, but think about what a standard error actually means. It means that the effect of the coefficient is like different from 0 or not, right? You could have a coefficient that is statistically significant, but whose effect might be really small, right? In which case, maybe the error is less affected by that coefficient, by the effect of that variable, by a really small amount. So even though it's statistically significant, it may get shrunk away because it has a small effect on the overall error.
It will be shaken away by the second piece.
Yes. Yeah, exactly.
But there are also scenario the coefficient really large.
Yes.
Then the p-value is also very large, which means it's not statistically significant.
Yeah.
Then I would assume that scenario would be filled out by the first part of that equation, right?
Yeah, but if it's highly uncertain,
That remains in the regression result. Is that so? Like if that
yeah,
noise
I
that's
think
probably is well, I shouldn't say doesn't, but
that's yeah. I think that's right actually. So this may actually somewhat favor larger coefficients.
inside of the statistical significant on top.
Yeah. But remember that that is related to your like x, and the fact that you're still like calibrating the betas, if it's not statistically significant, like this piece, it's possible that it could wash out, because you're like fluctuating across lots of different values of betas, and it might get picked up by another one of your variables. But yeah, I think it may be that, I think you're right. I think it may be the case that it would prefer, it would favor some of the larger coefficient values, as long as the error is getting reduced a lot.
But well, since this size remains very valid in the statistics, is that because like when we report the regression results, then even though those coefficients are still significant, if that's really small, we can actually take them away for some reason. But if the coefficients are really large, even though they don't show statistical significant impact, we can't really
Yeah.
take them away.
Okay, hang on. Yes. Yes, except, okay, so now that I'm thinking about it a little bit more carefully, things that are large that have still have a large standard error do have a higher likelihood of getting taken away compared to something that's large and has a smaller p-value, because if you think about what that essentially means, is that there's a higher variance in the spread of the data as it relates to that particular x, right? That's by definition kind of how it's figuring out that it has a large standard error, and because of that, you always have a value, a coefficient value that has large swings in the error, right? So what does that mean? So let me draw this. So this means something like if I have points that are spread out a lot, indicating that a line would have like a large standard error, you can imagine that the fluctuation of this beta, right, as it's trying to calibrate, can be really large. And as this slope changes a lot from like that to that to that, right, the size of the errors, like the distance from these x's to the line, changes a lot as well, right? Whereas if I had points that are all really, really close, and I drew a line through that beta is, yeah. So what does that mean? That means I can have a lot more flexibility to reduce the beta that could be large in number, but that, right, the slope is allowed to change a lot. And so when you have something that's less statistically significant, I can change this beta a lot more and get away with it. Does that make sense?
It does kind of do that.
Yeah. So it's actually saying, It's so I guess the way to kind of interpret that is like if your coefficient is really not significant, then you have more room to play around with that value. In other words, you may actually prefer to shrink it more because your error may not actually change that much because you have that flexibility to work with. Yeah. So in that sense, this equation is kind of inherently taking into account like issues related to the size of your standard errors. Yeah.
I'm trying to parse out why this is more optimal than a classical, like step forward, step back. Or what does this capture more acutely than the other two?
I would argue that this type of approach is a much more, I would almost say, objective way of measuring everything in like a single model. It's like you are able to run this all in a single model, and in addition, my ability to do something like this is actually a lot more flexible than with a step forward and step backwards regression. This automatically accounts for some of the interaction effects that you would miss in a step forward, step backwards regression. And when I'm dealing with 1,000 variables, even though that's a lot smaller than trying to figure out all the combinations, you are still talking about on the order of, a couple hundred models to run. Whereas here, I would only need to test out a handful of tuning parameters. So this scales even better than a forward and backward stepwise regression. And in fact, right, we know that this kind of arose out of a lot of the machine learning work, which is dealing with these big data sets.
So if I'm using the ridge approach, and the thing that I'm going to be adjusting would be the tuning parameter for each run.
Yeah, we'll see how to do that. Okay, ridge regression can be difficult to interpret if k is large, beta shrinks towards 0, but doesn't actually get set to 0. And so, because of this particular phenomenon, a common alternative to this is the lasso regression. So this is almost identical to the ridge regression. So let me write this out. Minimize RSS, which is equal to I equals 1 and yi minus beta 0. Plus lambda absolute value of beta. So this is absolute value instead of squaring. And the big difference here is when lambda is large, betas will be forced to 0.
this applies to ridge regression as well. Lambda is large enough, the betas will be.
No. That's the difference with ridge regression, is that ridge regression asymptotes to 0, whereas lasso regression will actually set the values to 0. And effectively, what this means is that with this type of regression, you can just say, this is almost like a combination, right, of ridge and my subset selection, because by setting it equal to 0, you're basically saying get rid of the variable.
Do you explain how in the ridge regression equation it was being asymptotically?
Well, we'll see it in a second. We'll see it in a second.
What was the reason for the difficulties in terms of ridge regression again? It was the.
It's because you're gonna have you'll have a bunch of betas that are really close to 0, but not actually 0.
Okay.
Okay, so let us go to R. Actually, I shouldn't close this. And let's take a look at implementing this. So we're going to do ridge and lasso regression. I'm going to make this a data table. And then we're going to get rid of ID. Okay, so for this part, you guys can just follow along. You don't need to code this part. I'm going to copy and paste a bunch of code just so that you guys can see. One second. And we'll walk through this. And I'll tell you what parts that you can sort of follow along on. Okay. Jumping back up here, here's what we're going to do. We're going to pick a value for lambda, which is our tuning parameter. We will perform cross-validation, some k-fold. We're going to obtain the test mean squared error, and then we're going to repeat steps 1 through 3 using a variety of lambdas. Okay? So this is analogous to taking a model, choosing combinations of variables, running a validation procedure. And essentially what we want to do is select the lambda, which gives you the lowest average test mean squared error. Okay, so like I've been saying, this is the procedure that we've been employing for cross-validation across lots of different things. So what I've done here is I have taken the the function that we've been working with, our k-fold function, and I've slightly modified it to specifically run ridge and lasso regression. Okay, so remember, we do our index, sample this. This is based off of the number of folds that we have. Then we have our for loop. And then I create my training set and my testing set. I'm separating the x and y's because of the way that these regressions like to put in their inputs. And then here, GLM_net is the function that will be running my ridge or my lasso regression. And so in this particular case, this is the ridge regression. So basically you have X and then a matrix of your X's and then Y, a matrix of your Y's. But we're doing it with our training set. Alpha is actually what determines if it's ridge or lasso. And then lambda is the tuning parameter value. I then do the same thing that we've talked about before, right? You do a prediction, then you take the average of the square of the prediction minus the actual test set. And we're doing a prediction based off of the test set, and we calculate our mean squared error. Okay. And all of this stuff is just storing the outputs from my model. So the values for lambda that I'm choosing to walk through are being done in orders of magnitude. So it's like value of 10, 100, 1,000, or well, sorry, by 0.1, so 10 to the 0.1. So it's going from like 0.01, 0.1, 1, 10, and so on and so forth. So you're really looking at orders of magnitudes here. So if I run this, what we see here, if I plot this, this is our average mean squared error and our lambda. So this is essentially that plot of model complexity versus total error. Okay, in this case, right, when I have a small value for my tuning function, the closer I am to the actual, just like running a linear regression. And as I increase the value of my lambda, the larger the total error essentially is. In other words, in this case, right, our test mean squared error. And so you're trying to find kind of the lowest point here. And if you do that, let's see. Let me get rid of this. So as I choose a different value of lambda for my tuning parameter, the beta coefficients will change in value, okay? And you can see that reflected here. At essentially a value of 0, if I just ran a linear regression, my coefficients would be, you know, these values, okay, for each of my variables. And as I increase the tuning parameter, what you'll see in the lines is that some lines will, some lines start going towards 0 faster than other lines. Okay, and so you can see that here, right? Like this green line here, which is in reference to age. That's that, or cards, yeah, probably cards. that stays up here for a longer amount of time than, say, your like ethnicity. It's kind of hard to see. You gotta zoom in on this part. But okay. Actually, you know what we can do? Here.
Make the lines.
Wait. We can do this. Plus y lim negative, let's say 10 to 25. Okay, let's try this again. Okay, cool. Now you can really see it. Okay, wait, let me go a little bit lower. We'll do minus 15. Okay, cool, perfect. Okay. So, what you can see here is that when you're overfitting, it will penalize certain variables first. And it will say, let's get rid of this guy, ethnicity Asian and ethnicity Caucasian, before we get rid of the number of cards that they have. Okay. Similar here, let's get rid of gender before we get rid of whether or not they're married. And, right, so your values may start here in your linear regression, but as you penalize the overfitting more and more, it's going to get rid of variables essentially at different rates. And so somewhere along here, I'm going to have the lowest total mean squared error, my total test mean squared error. And so I need to choose the point along my lambdas, and whatever lambda that is, that it corresponds to, that's like the best set of coefficient values that would predict your best mean squared error. Yeah?
I think it's cards, it goes up in the value
Mhm.
because the other non-significant betas are reduced, so it gets into the weights.
Yeah, exactly. Exactly, yeah.
And so the ones with smaller beta effects are approaching zero faster?
No, not always. No. So in fact, we can see that, right? In fact, we see this blue line versus this purple line. That actually has a larger effect than the purple, right, in your regular linear model. But that one goes away first, even though it's technically bigger. Yeah. So the size of the coefficient isn't always the main determinant of how fast it jumps to zero.
So when we're looking at this and you say select a point, right? Where you have your-
Select the line. So you
Select
can't
the
see
line.
that from here, from this plot. That's from the previous plot.
But you know, the lowest means where error. Don't you just select? Because if we look at the other plot and it's like asymptotic the other way, I don't know, where it's like goes to 0 to begin with, right?
Yes.
And not just select.
Well, you actually have to measure what the right lambda value is. So from looking at the actual numbers, I picked a lambda of 5.
Mm-hmm.
Okay. So let's look at this really quick. X not found, of course. Hang on. What did I do? Ah, okay.
When you set x to lambda, it does plus 5 minus 5 for the graph.
No, that was based off of the range of lambdas that I had chosen. Okay. Well, let me quickly look at this. Okay. So summary of linear model. So these are the coefficient values that we would start with. And that's what you would generally see kind of right here. And in this version where I set a lambda equal to 0, what did we say about that when the tuning parameter is equal to 0?
It's a standard OLS regression.
Yeah, so it's basically the same thing. So if I do that, summary, oh, I don't know if summary works. I think I have to do ridge coefficients. Yeah, okay, ridge $beta. Yeah, here we go. So if you look at the values of the coefficients here, they should be approximately the same as the values here. And that's, I say approximately because it might use a slightly different estimator. It might, this one may not be using the XTX inverse. But generally, these values are going to be almost the same. Now, let's look at what happens when we run all this stuff and we figure out what our best lambda is. Let's say the lambda is 5. Oh, let's see. Ridge $beta. So we can see that in the model that has the best tuning parameter as it pertains to our ability to predict, right, with the lowest test MSE, some of these values are going to be pretty close. Income is kind of close. Limit is pretty close. This is different, right? Rating is now almost double the effect. This one's a little bit lower. This one's pretty similar. And sort of so on and so forth. So it is like fine-tuning your coefficient values to take into account the fact that we want to like avoid overfitting. So it's going to change the effects that are coming out of the variables. Okay. And I can do a similar type of thing with the lasso models. So if I just run the same type of model, here's my errors. And then let's look at what happens with the coefficients here. I didn't run this. So similar type of thing, except there's something slightly different with the way that the convergence happens. And why don't we zoom in again? That's y lim, what did I say? Negative 15 and 25. So actually in this case, you can actually see the order in which the overfitting decides to eliminate variables, right? Whichever one hits 0 first is the one that it kicks out first.
They can't cross.
Well, the other one did, because it went negative positive.
Yeah, the other one did. So I'm not 100% sure, but I think that generally they can't cross.
Is it like
You know, it makes sense for the absolute value.
Yeah.
This is
Yeah, so this is the penalty function uses the absolute value as opposed to the square, and you get something like this. And here, again, you can kind of much more easily interpret the order in which variables get kicked out, right? So this one first, then this blue, the gender, then the two other purple ones, married and Asian, get kicked out. Oh, sorry, and then gender. This is student. Then student. Wait, no, student is the one up here. Sorry, the colors are close. I know. Okay, this one's education. This one is gender. So then education, then gender, then cards, then income, and credit rating. stays above 0 basically the whole time. So that might be like your most important one. And you can actually go back and compare, like, is the order that these things are getting kicked out kind of in the same order that I'm seeing in like the step forward progression. And that's a way that you can, you know, check some of this. But yeah. So you can see this is like a fairly different approach, and you'll get like very different values when you're doing this approach versus Ridge.
For rating, stays fairly flat and then slightly upticks. Is it because
Mm-hmm.
the variable cards and all the other, they're being dropped out, they're being kicked out, and that is sort
Yeah.
of towards the end causing that uptick in the rating?
Yep.
So would it mean that in the model's iteration without, I think, cards and I guess purple line is ethnicity, the effect of the coefficient of rating becomes more prominent as these variables get kicked out?
Yeah, that's right. And from my cross-validation procedure, I can identify a value of lambda that gives me my best test mean squared error, so in this case 0.211. And we can look at those coefficients, and they look like this. So again, these look actually kind of similar, right, to our linear regression value, but they are slightly adjusted, again, to take into account that the overfitting. So do you have to make this crazy function up here again to do your actual k-folds? No. In fact, that is built in, right? So where are we? So that's down here.
We'll have to make our own homework tree, right?
No, actually, I don't think so.
Okay.
Um,
Always one.
I maybe I'm misremembering, but
novel.
yeah. So this part you guys can follow along. This is pretty easy. So when I run, oh, sorry, I should mention the difference between ridge and lasso in your GLM net. So x equals x, y equals y, alpha equals 0 for your ridge regression, alpha equals 1 for your lasso regression. That's just the setting that they use. Okay, and so I can, instead of doing my whole taking this and shoving it through my cross-validation function a bunch of times with different values of lambda, I can just do cv.glmnet, which stands for cross-validation. So this function will just do that for you. Okay? So if I run this guy, let me get rid of all this. It will run across a range of your tuning parameters, and then it will identify the best lambda.
What's the 11 on
Is that the number of variables?
I think that's the number of variables. I don't know why it does that. And it can auto-generate your coefficient plot. So this is the exact same plot that we had from before, but the one that I made looks nicer. So you'll have that code available to you. This will all be posted online. You can look through it. Ridge auto. So we can go back to glmnet, and from ridge.best you can do $lambda.min. So this returns the tuning parameter, lambda. Lambda.min gives you the one that has the lowest test mean squared error. And so if you set that equal to that, then you can run your GLM net, and we can observe ridge.auto beta, and it will give you the one with the best. So it just so happens that this one is actually different from the one that I had made because the range of lambdas that I tested probably was less sufficient than the one here. So that is one tricky part of like doing it manually, is like actually figuring out the best range for your lambda. And we can do the same thing with the lasso regression. Here, that's what the errors look like because I changed my tuning function or tuning parameter. These are the different points at which my betas drop to 0.
And on top you can see the variables being dropped. Is that
Yeah.
significant?
Yeah. So if I do this, lasso.auto $beta. In this case, it's actually not dropping anything to 0. It says we should keep it all in, and we're still okay in terms of the overfit. And actually, in this case, you can see the coefficients are a little bit different.
Why was it the case that in the ridge regression, as you go increasing the lambda, no variables were being kicked out? Is there a point after which being kicked out, or it's because they were only asymptotically, the coefficients are asymptotically approaching 0, so no variables will be dropped out?
In the ridge?
Yeah.
Yes, in the ridge you won't drop variables, but in lasso you will. In this particular example, we don't drop anything, but it's perfectly reasonable to see that happening in other models. So again, to sum up, right, our ridge and lasso approach is this alternative to the subset selection where we're doing this forward backwards, we're doing different combinations of variables. In this one, you just throw all the variables into your model and then let it figure out which ones actually kind of make a difference in reducing the total error of your model. And you let the model automatically figure out which variables are important. Okay, and so as you scale up to even bigger data sets, right, the reason why these tools were created, right, with the initial classical methods, subset selection, you're talking about on the order of, getting to tens to hundreds of variables. That process of 2 to the n gets reduced by quite a bit. It just, the cumulative sum, k variables, the number of combinations, k plus k minus 1 plus k minus 2, and so on. So that's a lot reduced from 2 to the k. And then here, it's even smaller, right? So this type of approach can take over from what a stepwise regression would be able to do when you're talking on the order of tens of thousands, hundreds of thousands, or millions of variables. Like this is a procedure that is a very powerful way of doing essentially a selection method to figure out which variables are kind of the most important for predictive purposes. Yeah.
I'm assuming that lasso and ridge work for non-linear functions, like just like or binary or anything like that, or does it just work for linear?
The formulations that I have shown are particularly geared towards the linear regression, but you can imagine this idea of having like a penalty function is not unique to linear models. Yeah. And so, so you'll see variants of this type of thing employed in lots of different models. Yeah. Yes.
In the second plot command, what do the arguments x, var, and label do?
Yes. So here, what you're plotting are the coefficient values. That is what this thing is. So if you do glm net.fit, that should give you essentially a table of the coefficient values that change as you go across different lambdas. So you're setting your x equal to your lambda values, and then we're observing what happens to those coefficients. And I think label is just the setting for a bunch of these labels. Actually, we can see. I don't know actually what happens if I delete this. Did anything change? Oh yeah. Yeah. So watch right here. So this refers to variable number 8. Yeah.
Cool.
So there's 11 variables, so 8 is a student. So this is whether or not they're students. Yeah.
So if we apply the lasso or bridge into a data side, the specification of the regression model would be very much like a linear.
Yes, yes, that's right. So the interpretation of all of these things is the same.
Okay.
So this would be, as income increases by 1 unit, the average balance goes down by -7.7. As your credit limit increases by 1 unit, the average balance increases by 0.2. So yes, in this case, it's very much in the same interpretation vein as a linear regression.
Oh, it's much more like a model selection criteria.
Yeah, so okay, so technically speaking, the terminology is this would not be a model. Wait, okay,
Yeah,
let me make sure.
confusing because it's called regression. It's not called some metric. It's
So,
not like a
yeah.
regression.
So when we talk about selection, what we're talking about is whether or not to include certain variables. But in fact here, you include all the variables. And the proper term for this is regularization, because you are essentially regulating or changing the size of the coefficients of the variables in order to determine the whole thing about overfitting. Any other? Yes.
So when we do a lasso or a ridge, are we like, is it proper to say this is what our lambda is? Like, what's like the best practices for like describing your?
You would have your standard regression table, and then you would have some value of your lambda being reported. And you just say that it's a ridge regression or a lasso regression.
And there's no other like interpretation that you need to like do.
Well, there's like all these other values. Let's see. Lasso, best. Wait, summary. How many M's are there? Summary, lasso.best. Right. So things that you could report. Information about your tuning parameter, information about your cross-validation procedure. Like this is your mean of the error term, the standard deviation of your error term, the upper and lower bounds, I don't know what n0 is. Your fitted values, so these would be your coefficients. The distribution of lambdas that you tested, the best lambda value that you found. And I think that would basically be
That
it.
would be fine.
Yeah.
That would be fine.
Yeah.
What's the upper bound of the cross validation? Is the upper bound MSC? Or?
Yeah. It should be the largest value.
In the MSC.
Yeah, actually, I don't know if they report the largest value or the like 95th percentile largest value. Yeah, but I mean, either of those would be fine. All right. One more question.
Yeah, one more question. So let's say you look up the summary, right? You call it a summary table. What's like one or two indications from the data that's presented which would tell you that I did something wrong, my model's wrong, something looks incorrect, like the relationship between variables.
Yeah. So validation type of things is that I would run your lasso and ridge. I would look at the coefficient values. I would compare them to a linear model to make sure you're like even reasonable. Like you could set the lambda equal to 0 and just make sure that it's matching your linear regression. Yeah, and then you could always do some predictions and see how well it does, right? Compared to other procedures, you could do stepwise regression and see. This should always beat stepwise. It should always beat stepwise, right? Because think about what it means to do stepwise. Like this thing where I'm allowed to futz around with the actual values of the coefficients, at the very least, if the stepwise regression resulted in the best possible model, like both your ridge and your lasso should be able to reach at least that same value, if not better, right? So, strictly speaking, from a like test MSE predictive ability, these will always be better than stepwise.
So in terms of a process, you should be always start with ridge or lasso, either one, depending on what you do, and then you say, okay, great, did it, and then validate against the stepwise, or should you just do stepwise first, do it, and then do ridge?
I don't know. It's you have lots of these I'm giving you all the tools, and then you can figure out how to use them.
Okay.
All right.
I had a question about dome.
Yeah, one sec. Let me stop the recording.